Okay, so we are done talking about the inner solar system and the terrestrial planets, as we just finished talking about Mars, which means we're going to move outwards, further away from the sun, and talk about the Jovian planets. That term Jovian is the one that we will use almost exclusively to refer to this grouping of planets. You might also know them as the gas giants. That's a term that gets used quite a bit, but the more scientific term is the Jovian planets instead of gas. Here are the planets we've been talking about so far, the terrestrial ones. This is a 2-scale image showing how much smaller Mercury, Venus, Earth, Mars, and the moon of Earth are compared to the gas giants. They are truly giant. The Jovian planets are much larger in a different category, so it makes sense to talk about them separately. The way that we will approach this topic is to talk about their cores. So what happens on the very inside of the planet as we move towards the center of each of them. We'll talk about the ice and metals, which will continue our discussion of the cores. We'll talk about their atmospheres. Notice that there is no discussion of their surfaces because the Jovian planets have atmospheres and they have cores, but they don't have a surface, which might seem wrong-headed. How does that work? How do you go from atmosphere to core without having a surface, let alone a mantle? Well, we'll see what that looks like. And maybe you can start to imagine by just thinking about, kind of some of the properties that we've been discussing, some of the physical parameters. We'll also be talking about magnetospheres. We hadn't talked about magnetism recently. We completely didn't talk about it when we talked about Venus and Mars, although Venus has a really light magnetic field, somewhat like the very weak magnetic field of Mercury, which we did, discuss briefly. Regardless, there wasn't too much to talk about there. And that was in contrast to Earth, right? Earth has a magnetic field. It's, something that we're familiar with, relevant to understanding a compass and so on. So we got into it. Hopefully we'll be able to leverage some of that introduction that we did with magnetism when we talk about the magnetospheres of the Jovian worlds, because they all have them. And in some cases, the magnetic fields created by the Jovian worlds are really dramatic and strong and really big characteristics of the solar system as a whole, let alone just the planets themselves. Speaking of which, we'll talk about the role that the Jovian worlds play in the solar system. So, as we like to do when we talk about planetary science, we like to summarize the characteristics. And before we do that, let me ask you a question to see what your expectations are, your intuition, or your background knowledge. So, compared to the terrestrial planets, the Jovian planets have, right? So you got mass over here, larger, 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 smaller, smaller, and then density, about the same, larger, smaller, larger, smaller. So which combo of mass and density is correct for Jovian planets compared to terrestrial? Yep. Oh yeah, taking more than one summer class. That's like me teaching more than one summer class. It's a lot to balance. Because I teach, the 2 sections I always talk about, and then I've sort of hinted at, but I'll just come out and say I'm also teaching a 3rd section of this class for another school, but that one's asynchronous, so no meetings. At least it's all the same class. Okay, so I got Alara, Isabel, Nicholas, all saying the combination is number 3, larger mass, smaller density. Well, it turns out that you are all correct. Very good. Glad that you recognized or remembered that the density is smaller. They're lower density worlds. And just kind of think, well, they're gassy, right? Gas is not thought of as something very dense. So if you have a planet which has a lot of gas, well, that's going to bring the density down. And if we're talking about density and mass, let's take a look at them in our table. So this is the characteristics that we always summarize when we talk about worlds, the same ones that we've seen for Earth, Mercury, Venus, and Mars. but now we're going to see it all at once for the 4 Jovian planets represented in this table. And those characteristics are mass, radius, density, orbital period, semi-major axis, rotation period, and orbital tilt. So the exact same ones. So the 2 that we already have thought about are mass and density. Well, let's look at some standout numbers here. One is that Jupiter is 318 times the mass of Earth. That is a big planet, right? That is a lot of mass. And in contrast, Saturn, big, but not nearly as much so. Saturn has a mass that is only 95.2, only, right? The mass of Earth. So it's not even quite 100 times the mass of Earth. It's downright small. Although, if you're talking about small, Uranus and Neptune really are in a class of their own. Their masses are similar to each other, and they're going to both be significantly smaller, about 5 times less massive than Saturn. And this grouping of Uranus and Neptune, we will see quite a bit. It is completely natural and sustainable, like scientifically, logically, to group together Jupiter and Saturn, sometimes for the purpose of contrasting them, because there are, as we can see, some key differences, but they have a lot in common as well. And what they have in common, they often don't share with Uranus and Neptune. Sometimes I've heard, for the purpose of mentally separating the 4 Jovian worlds, is a name given to Uranus and Neptune, calling them the ice giants instead of the gas giants. They are colder. Indeed, they do have more ice, and their cloud layers are more frozen than just like typical clouds. And so in that respect, the name is appropriate as much as it can be, and it definitely helps separate them, okay? So think about those separate groupings to help you remember. Okay, now, what's interesting is if we take a look at the size, and actually this is going to segue into density, let's just look at the size of Saturn and Jupiter. Well, I just pointed out that Jupiter is significantly more massive than Saturn, over 3 times. But their sizes, measured in Earth radii, are not that much different. You could say fairly accurately that they're both about 10 times bigger than Earth, right? There's a difference, right? Saturn is closer to 11, rather Jupiter is closer to 11, Saturn is closer to 9, But that's not a 3-fold difference by any stretch of the imagination. So why such a big difference in the mass? It's this difference in the radius, even by cubing and showing the cubic relationship between radius and volume, doesn't support having so much more mass. And we see that with the densities. So check out the 2 densities. Jupiter has a density of 1.33, Saturn only 0.69. So we have a case where we have comparisons between mass that doesn't equal, density that doesn't equal, and radii that are comparable. Okay? So Jupiter is significantly denser than Saturn. But now let's quickly include a comparison of Uranus and Neptune to see that Jupiter has a density that's actually more similar to that of Uranus and Neptune. So really the standout density is Saturn's, where that value is quite low. Saturn is exceptionally low density. It's the only planet with a density less than water. It's the only planet that can float. You just need a really big bathtub to put Saturn in. The orbital periods, what about them? Well, this is directly related with semi-major axis, because as you know, we can just take these 2 values and say if you know one, you know the other, because you've got Kepler's 3rd law that says that p squared is proportional to a cubed. So you have that direct proportionality. We can use it perfectly to compare between planets because they all orbit the same sun, right? The same star, our sun. So we don't have to worry about the Newton's version of Kepler's third law, where we actually have the constants included. Instead, we just need the proportionality. And that, at least if we are going to, compare to Earth. Because if we know Earth has a value of 1 year as its orbital period and 1 AU as its semi-major axis, well, there's our numbers that we can just compare to. Okay? So, for example, if you knew that Jupiter was 5.2 times further from the sun than Earth, 5.2 times, then you would be able to plug that value in for A and solve for P. Okay, so you could directly solve for P, which would be A raised to the 3/2 power by plugging in the 5.2. And if you did that, what would you get? You'd get 11.86, the orbital period. Okay, already in years because it's set up to be in years with comparisons. And you can continue to do so if you know one value or the other. If you knew the orbital period but not the semi-major axis, well, then you could, of course, solve for that unknown. And what do we want to take note of here? Well, the orbital periods are long. Of course they are. They're further from the sun. It takes a long time for them to orbit. That's quite a circle that they have to cover. And the orbital period and the fact that it grows so much is not only that the path is longer because the circumference of the orbit is longer, but the velocities go down because as you get further and further from the sun, the gravitational tug is less. Therefore, the velocity necessary to sustain a stable orbit is less. So, which is actually why P increases with A raised to the 3/2 power, right? That nonlinear increase and a larger increase than that of A, which is raised to the 2/3 power, right? Less than being squared as opposed to the other one being, in fact, less than linear in the case of A, whereas the other is greater than linear. And what that really means in practice is that just you have this more dramatic increase in the orbital period. It goes up quicker than you would expect if you just assumed it was a linear increase, a straight line, just hey, double the distance, double the period. We know that's not the case. And that's how we end up getting these, really large orbital periods for distant planets. Neptune takes 164.82 Earth years to complete a orbit around the sun. So no human can live long enough to experience a whole Neptune year, right? It's just too long. A Uranus year is, attainable within a human lifespan, but on the upper end of it, 84. Saturn, almost 30 years to complete an orbit, right? So you kind of think, many of you haven't been alive for one Saturn year, So it's you'd still by Saturn year standards, if that's somehow related to a life form that had life stages like ours, but scaled to that year, you'd be an infant, less than a year old. Okay, and the semi-major axis values aren't as dramatic an increase as I was trying to express. Hopefully makes sense to you all. But they do have something noteworthy, that they're quite far spaced. And the spacing isn't itself like even. So the spacing between the gas giants gets wider as you get further from the sun. In particular, going from Saturn to Uranus is a much larger step than going from Jupiter to Saturn, right? So we can see that Jupiter at 5.2, Saturn at 9.5, so a step of about 5 astronomical units, also almost doubling the distance from the sun. But then to go from Saturn to Uranus, the distance gets doubled again. So the step is 10 AU. The next step is just a little bit greater. So it is technically still going up, but not nearly as much. And it's about another 10 AU to get out to Neptune. So we find that the gas giants, the Jovian worlds, get more spaced apart the further from the sun you go. What about the time it takes them to spin on their own axis? And for that matter, we're talking about their spin, right? Their rotation, because rotation, we also call spin. Well, what about the tilt? Well, they all have some tilt, Jupiter the least, but going back to the rotations, they all spin quite quickly. Okay? So their orbital periods, the time it takes them to complete a full orbital period, their rotational periods, so the time it takes them to complete a full spin, right, turning all the way around on their own axis, is always less than an Earth day. With the terrestrial planets, we had, these really slow days for Mercury and Venus, right? They both had these incredibly long days, really strange rotations. But the Jovian worlds don't. They actually all have rather fast rotations. They all spin quickly and with similar values to each other, right? Saturn and Jupiter, each takes them a little bit less than half an Earth day, so around 10 hours each. In the case of Uranus and Neptune, more like 2/3 of an Earth day, so probably around 16 hours to complete a full turn. Considering how big these worlds are, that means that, it's pretty impressive, right? There's a lot of rotational energy in them. They're really turning, okay? Which has to do with their formation. The way they were formed kind of means that they have, by their very nature, a lot of spin, which is not unlike the sun. The sun spins quickly as well. Their orbital tilts are a different story in terms of making some generalization. We just can't. They all kind of have different orbital tilts. Jupiter has very little of one. We could maybe speculate that has to do with the fact that it's so big and it's just, it's essentially aligned up with the ecliptic plane in the sense that its rotation is, in the plane and its rotation axis is perpendicular to the plane. That's what I mean by alignment. In the case of Saturn, pretty significant tilt, kind of like Earth or Mars, although that's about the only comparison you can make between Saturn to Earth and Mars. Uranus has another one of those really strange tilts, which is, what's the only other planet we saw with a very dramatic tilt? Well, it was Venus. Venus was upside down, right? Completely pointing the wrong way. Well, Uranus isn't upside down, it's on its side. So it has almost a 90-degree tilt. And since it's past 90, it ends up being that when you look at it from the prescribed direction for, determining rotation, it's actually rotating in a prograde direction. That's why it shows up as a negative value. But it's pretty subtle. And so it's not, I don't really think about it that much. I just think about it as being on its side and thinking about it as neither being prograde nor retrograde. Oh, I meant to say it's retrograde. And the reason that I call it retrograde is because if you looked at it, it would be clockwise rotation, at least partially, right? But mostly it wouldn't, the rotation is just completely at 90 degrees. Only a small component, so to speak, is actually, either prograde or retrograde. If you look at Neptune, again, pretty significant axial tilt, as again being, like Saturn. So Uranus will be one that we'll talk about. It has weird effects in terms of how it actually points towards the sun. If you want to think of the three planets that have interesting considerations between the interactions of their rotation and their orbit, those three planets are Mercury, Venus, and Uranus. I often ask questions about the interesting way that those alignments work. Okay, now moving right on, as promised, to Jovian cores. So we've got our 4 cores shown down here because we're going to add to this image. Jupiter has a diameter of 7, Saturn 8, Uranus 8, Neptune 10. So what's it referring to? 7 what? Okay, well, it's referring to a distance in, I think, hundreds of kilometers. So this is 700 kilometers 800 kilometers, 800 kilometers, and 1,000 kilometers, or 1,000 kilometers. And here's Earth, which is 600 kilometers. And it comes from a figure in the book, and there's a scale there that says, what the values refer to. And I think the 100 kilometers sound right because our whole planet is 6,000, and I think our core is about a tenth of that. So I believe that where that number comes from. But more importantly, for our considerations, we just care about the relative values. The fact that 7's a little bit bigger than 6, 8's bigger than 7, and so on. Okay? So what this is telling us is that if you took Earth and you put Earth inside of Jupiter or Saturn or Uranus or Neptune, in each case, Earth would be smaller than the core of those 4 Jovian worlds. So all 4 of the Jovian worlds have a rocky and metallic core, so composed out of terrestrial planet material, the material that we associate with terrestrial planets. All 4 of them have it, and all of them are bigger than Earth, with Earth being the biggest terrestrial planet. Okay, there's Earth for comparison. All right, here are the cores scaled to Earth. So imagine that each of these just represent the actual core, the rocky and metallic core of that Jovian world. All right, so we shrunk it down. Jupiter has the smallest, okay, but also the most compacted. All of them are highly compacted. They're cores after all, okay? So none of them would have densities equal to Earth's. Okay? So I've mentioned this before about the proportionality between volume and radius, and it's cubic, okay? So if we have this relationship here, right? If we're saying that Jupiter's core is a little bit bigger than Earth itself, Saturn's core, Uranus, all the same, right? Getting progressively larger. Well, then what does that mean for their actual volumes, right? Because after all, these are all radii. So if we take each of their volumes and we cube them, then we can show what value we get. So if we cube the volume, again, this is sort of this dimensionless volume, or at least in units that aren't specified, 6 cubed, we get 216. All right, so that would be the scaled volume of Earth. Do the same for Jupiter. 7 cubed is 343. Plug in your calculator. This is indeed what you get. It's cube of 7. All right. 8 cubed, 512. Same for Uranus because their cores are about the same size. And then finally, 10 cubed, of course, is 1,000. That one is easy to think of. All right, just 10 raised to the 3 power. That's where the 3 zeros come from. And that's the core of Neptune, the biggest of the Jovian cores. So then, to compare them to the volume of Earth, the volume of Jupiter's core, 1.6 times as big, right? And notice, right, it's 7 over 6 is its linear comparison, because that's comparing its radius, but its volumetric comparison is more dramatic. That's been a common theme, right? And so it just reminds us that depending on what we're asking, we have to be careful about whether we're comparing radius or we're comparing volume or we're comparing mass. Because if you compare the wrong one, the comparison could easily be misleading. Okay? So here we have, but a reasonable comparison, 1.6 times the volume, Saturn and Uranus, 2.5 times the volume of Earth. And again, we're talking about their rocky cores. And finally, Neptune, its core, 4.6 times the size of Earth. So the largest rocky object in the solar system is what? You tell me. Okay. Very reasonable guess. All right. So we got a 1, a 2. Venus is big. But we've got 3 5s. So majority of 5s, Nicholas, Anthony, Alexander. Well, it turns out that those of you who said 5 are right. This is a real gotcha question, right? Yeah, oh yeah. Yep. And that's it. The terrestrial planets, they just don't have anything to compete with the Jovian planets. To put it another way, the Jovian planets, they beat the terrestrial planets at their own game. Not only are they bigger in every possible respect, as we saw, just they're including all the gas, even if we exclude the gas, they still beat the terrestrial planets. They have more rock and metal. All right. But they don't have surfaces. So that's the one thing that terrestrial planets have. That's their claim to fame. Okay. Well, what's going on with these cores? And the reason we know we're still talking about Jovian cores is we're talking about ice and metal. Well, we're not going to find much ice, and we're not going to find any metal in the atmosphere of the Jovian planets. Instead, we're going to find it near the core in the interior. All right, so we're now going to work our way out from our starting point of the very center of each world. So sticking with our comparison. Oh, I finally thought of it. These values, because this is an entire Earth. So before I misspoke and I thought, oh, this is the core of Earth, but I should have known it wasn't, because afterwards I contradicted myself and I said, hey, we're comparing to all Earth. So on the one hand, I knew it, but just got ideas mixed up in my own head. Sorry for that. But point being is that this is the entire Earth, which means that this 6 right here, that it's referring to 1,000 kilometers. So each of these numbers refers to approximately 1,000 kilometers. So each number you see is about 1,000 kilometers, that is. Yep. All right, cool. So Jupiter, we've already talked about its core, Saturn's core, Uranus, and Neptune. Now let's add other layers. So for Uranus and Neptune, we're adding a layer to show ice. We're also doing that for Jupiter and Saturn. For Jupiter and Saturn, we're showing a layer that doesn't exist for Uranus and Neptune, which is the metallic hydrogen layer. The reason we're doing that is because we're talking about metals. All right. So the rocky core, right, dense material, absolutely has metals in it. Okay. So I don't want you to think there's no metal in any of these cores. It's all the densest material. There's going to be significant amounts of iron in that rock, absolutely guaranteed. But it has the property of really like not conducting like a metal. So it's a mixture, and it's not going to be a conductive core. So all the cores of the Jovian worlds, think of them as not conducting electricity. So in that respect, they're not behaving like metals, despite the high densities they have. One number I'll just throw out there, because I don't think the slides include it, and just interesting fact, is that we talked about their sizes, made a big deal about it. And it's a great way to remember, right? Whoa, Neptune has more rock, than Earth. Well, what's interesting is that they're all also much denser than Earth. I kind of mentioned that in passing. And one value that I remember seeing is that Jupiter, right, its core is about the same size. It's the smallest of the cores, right? But it's also the densest. So that size is only half the story. And it's 10 times the mass of Earth. So this 7,000 kilometer rocky core of Jupiter is 10 times the mass of Earth. So that means it's 10 times as dense as Earth, which, if you remember, Earth was about 5.5 grams per cubic centimeter. Then it's about 50 grams per cubic centimeter for the density of this rock core. So it's not rock in a common state, right? This is super compressed dense rock. Above it is incredibly pressurized ice. So this is material that has been compacted into ice despite being high temperature. And all of these are high temperature ices that are only forced into an ice state because of the pressure. They're forced to be a solid, despite what you typically think of as plenty of temperature to phase change them into at least a liquid, let alone a gas, right? Composed out of significant amounts of water ice, right? These are all predominantly water ice layers, right? But super compressed water ice at high temperature. Above, now, I started talking about this, but to get back to it, the metallic hydrogen, and the reason I kind of talked about the cores because I want to talk about metals. Well, this idea about having a metal layer for Jupiter and Saturn and it coming from hydrogen is strange and initially difficult to wrap your head around. Because hydrogen is a gas, right? It's the lightest element. It's the gas that always escapes into space. Well, hydrogen is also going to be the primary building block of all four of these worlds. No surprise. And there's a lot of hydrogen around in these planets. In their interior, they have, just because of differentiation, they have layers where hydrogen has been compacted by the layers above them. And it has been pressurized to the point that the hydrogen became a liquid first and then a solid. So this is solid hydrogen. And as a solid, hydrogen acts like a metal in that it freely conducts electrons. So that's why we call it metallic hydrogen. It's also just solid hydrogen. It's essentially hydrogen ice, but it's hydrogen acting as a metal in the conductive sense. And that's why the term commonly gets used. It's not a phase of hydrogen that is easily made on Earth. Only the most sophisticated labs can actually produce enough pressure to create metallic hydrogen, and only on very small scale in order to explore its properties. So the ices: solidified gases, liquids, methane, ammonia, some H2O. Okay, so it's not primarily. Okay, I misspoke. So it's mostly methane and ammonia. Okay, the metals. So, to define a metal, you have atomic nuclei in a grid with electrons that are free to move around. That's what I mean when I said that metals are conductive, metals have free electrons. Here's the electrons moving around. So in the case of hydrogen, here's a background question. Most hydrogen nuclei are made of what? It's a good point to ask this. And maybe but I haven't recently given it away. I say it's a good point to ask it because we're going to be talking about hydrogen again when we talk about the sun and stars. So what is it? Hydrogen, the lightest element, 1 on the periodic table. Alexander and Nick say it's 1 proton and 1 neutron. Everyone agree? All right, Alara says 1 proton. Okay, so Alara, you're right. And those of you that said, one proton, 1 neutron, I totally get it. I thought that too for years, and then finally really I came to appreciate, what it means that it's just 1 proton. That's hydrogen. That is the most common form of hydrogen by far. What we mean by hydrogen is just a single proton. It doesn't have a neutron. That seems wrong because we always talk about atomic nuclei being protons and neutrons. Well, they are, except for hydrogen. Is it possible for hydrogen to have a neutron? Yes, and it has a name. It's called deuterium. So deuterium is an isotope of hydrogen, and it's somewhat common. It's a tiny percentage of the natural population of hydrogen, but is out there. Heavy water is composed of deuterium and oxygen. because that's the thing about isotopes. You can form the same molecules. So actually, that's what people mean when they talk about heavy water, which is used like in fission, nuclear power. But that's the unusual state of hydrogen when it has one proton and one neutron. There's even tritium, which is one proton and two neutrons, which is a highly unstable state of hydrogen that can be created through fusion and fission, but it never lasts for more than a split second. Yeah, but easy mistake to make. You say whoops, but yeah, and maybe because you knew in the back of your head, but yeah. So interesting thing about hydrogen. All right. So when you've got a bunch of hydrogen together, when the pressure is high enough to force hydrogen nuclei into a rigid grid, the electrons are free to move around them. You end up with a grid of just individual protons and the one electron that would have existed in neutral hydrogen atoms. And there is your hydrogen metal. Not the typical metal that you think of for conducting electricity, but absolutely is what exists inside of Jupiter and Saturn. All right. So I'm going to continue into atmospheres at least a little bit before our break, in the interest of getting through a good amount of content. Let's move out from the metallic hydrogen. Okay. So if we talk about the core, it would typically include the, everything below the metallic hydrogen for Jupiter and Saturn, right? As since we split sections. So is the core just the rocky core, or does it include the ice? It depends on the context. I would always specify, and because there's no absolute agreement. Sometimes you might say the rocky core, or different layers of the core. But despite the ambiguity, it would be made clear depending on what question is asked. And once you get to molecular hydrogen, you are clearly in the atmosphere. You're not in anything that would qualify as the core of that Jovian planet. And this gets into sort of that open-ended idea that I presented at the beginning of the lecture, which was saying, what does it mean that they don't have surfaces? Well, the way I would say that is that it just means that they have this gradual change from gas state to, more pressurized gas state, eventually becoming pressurized enough that the state is a liquid, that different molecules are forming, that there is some sort of, precipitation happening, some exchange, some convection, some processes as you get further down. The heat has gone up dramatically as well. And then eventually it becomes such a highly pressurized, high temperature environment that you get this phase change to, strange things like metallic hydrogen or, super dense methane and ammonia ice. And it's all gradual. It'd be all highly deadly to humans. The pressures would kill us first, the temperatures second, but none of it would be, survivable in any sort of, just jump, if you want to just dive into him in a spacesuit, it would just, if you did have a highly, pressurized, stable spacesuit, then I guess gradually you would see everything get denser and hotter around you until eventually just it melted your spacesuit. So that, so it's just this layering and layering, and the sheer size, the sheer weight leads to dramatic effects that are real different than what we're used to, But then, of course, that's the molecular hydrogen level of each of their atmospheres. That's the bottom of the atmosphere. So denser level, right, containing significant amounts of hydrogen. getting denser and denser as we go down. And really, the only thing we're going to add to this is going to be the cloud layers on top. So this molecular hydrogen is like the big level that sits on top of either the ice or the metallic hydrogen. This is sort of showing the splits in numbers. So it's just summarizing the values that would be associated with these different cones into the worlds. So with Jupiter, it has less atmosphere proportionally to its metallic hydrogen than Saturn. Saturn is mostly atmosphere and a small band, right? A small layer of metallic hydrogen, almost like acting like a mantle, right? And if you think of comparable levels on Earth. Whoops. And with Uranus, they don't have, neither does Neptune. So Uranus and Neptune do not have a metallic hydrogen level. That's one of those things that sets them apart, right? And then the proportional thickness of the ice, real small for Jupiter, significant for Saturn, but on the small side, and then quite large, a defining characteristic of the entire volume of the planet for Uranus and Neptune. These numbers are going to help explain a few things. They're going to the significant amount of ice, that ammonia and methane ice, which now I realize I should have, thought that it was primarily ammonia and methane and not mistakenly said it was primarily water ice, because I know those are the ices that are thought to create the magnetic fields of Uranus and Neptune, are those ammonia and methane ice levels, which are a significant portion of those two planets, and not the creation of the magnetic field for Jupiter and Saturn, because where's their magnetic field created? I'm jumping ahead a bit, but you'll see this again in a minute. The magnetic field of Jupiter and Saturn, they're created by their metallic hydrogen levels. So that's why kind of the size of the metallic hydrogen, how much of it exists, is going to matter. The other thing that we've already seen that these numbers help explain is the mass of Jupiter. The fact that it's not much bigger than Saturn, but yet much more massive. And that's really clearly indicated by how much of Jupiter is this metallic hydrogen, how Jupiter is essentially a super compressed version of Saturn. And so its mass was added to Jupiter, but it didn't increase its size. Instead, it just caused it to cave in on itself more and create much more dense matter within than Saturn. So as Jupiter was created, you could imagine at some point it would have passed through a Saturn stage. But as matter was continually added to Jupiter, it didn't get much bigger, it just got denser. Okay? And of course, the layers of the planets correspond to density changes. As you go deeper, you get more density. What's that called? That's differentiation. These worlds are fully differentiated. They're planets in that respect, absolutely. No surprise, considering how big they are. They're all fairly low density, though. Despite the dramatic, amounts of rock and everything, the still significant amounts of atmosphere and the fact that metallic hydrogen isn't that heavy contributes to their overall low densities, with Saturn being real low. So what molecule is the main component of the primary atmosphere? Well, hydrogen. You can tell it's already put in bold. Okay, but we've seen this enough times. I think you probably got it cemented in your minds. Every single planet started with the same primary atmosphere. All right. Well, what about the primary atmospheres of the gas giants? The same, right? Because that was the logic. That was the totally justifiable argument, was that the primary atmosphere had to be shared by all planets. And the Jovian planets were no exception. But I've been waiting to say this for a while, so I'm excited. They kept it. They didn't lose their primary atmosphere. They never went through a secondary atmosphere phase because there was never some, solidifying of the surface and escape of hydrogen and helium. They went a totally different route. They were able to hold on to their primary atmosphere. and instead just grow it and just pull in more of those primary building blocks. How? Well, because they were in a place in the solar system where that was possible. We'll talk about that later, though. All right. So why did they keep it? Well, this is part of the story. I'm gonna, think of an answer, but I won't check the chat. So think about what you would say, because I just implied that there's got to be another explanation about their location in the solar system. And when I said that, I knew that that's crucial, and we're going to talk about it. But in the back of my mind, I'm thinking, oh, well, also there's the whole gravity thing, but they go hand in hand. And this question is just asking about the role of gravity. All right. So they have, well, although it does mention cold, good. So they have the large mass and are cold. So these two criteria are what allowed the Jovian planets to hold on to their primary atmosphere. But you can't have one without the other. Because if it's just large mass, then why aren't there gas giants closer to the sun? Right? Because there could have been, the mass could have grown. If it's just a matter of like chance collisions to get a big enough, planet, a few big enough planetismals to start a big chunk that pulls in more matter from gravitational attraction, there's nothing that says that couldn't happen anywhere. But yet we only see them further from the sun. And that's because they had to also be cold. It wasn't enough to just be massive and to thus have more gravitational pull. They had to be surrounded by cold enough solar system for those primary atmosphere building blocks, that hydrogen and helium, to largely form ices, at least ice in the vacuum of space. And I know that we have a chapter coming up that's going to really spell this out, so I don't feel any need to get into it too much, but just foreshadowing things to come, that's going to be the key idea, is this defining distance from the sun, often called the snow line or the ice line, where hydrogen and helium in between planets is able to form ice, whereas hydrogen and helium in between planets, so in the near vacuum of space, in that vast emptiness between planets, doesn't form an ice. What I will say is that you might be thinking to yourself, well, why would it form an ice anywhere in the vacuum of space, or why wouldn't it for that? Maybe you're thinking, why wouldn't it, right? Because isn't space supposed to be super cold? Well, as some of you might know, there's this weird thing about space, right? And when that you see in movies where they show people going into space, and without a spacesuit for a second, which is somewhat possible, but highly damaging your body. Space on the one hand is really cold because it doesn't hold any heat. There's nothing to conduct heat. So all of your heat just immediately starts radiating away. And so you start freezing. You're immediately, your skin just gets frozen, right? That heat just disappears. But at the same time, space is full of all this high energy light. So if you're facing towards the sun, then, and that intense sunlight is hitting you, it's able to deliver quite a bit of energy. So you can start freezing while simultaneously getting a sunburn. Those things don't, contradict each other, and both would happen simultaneously if you were both facing the sun and in the vacuum of space. So that idea about the intense sunlight is why if you put, say, a droplet of water into space in near the orbit of Earth, so that distance from the sun, that droplet of water in space wouldn't freeze, okay? At least not permanently. It would instead turn into a gas, because as it gets hit by the sunlight, it's enough to turn, to phase change it into a gas. So any H2O that exists in the near vacuum of space in an Earth orbit is going to eventually end up as a gas state. It will never clump together into little ice crystals, because it would initially, sure, right? And even occasionally. But over the long term, all those ice crystals will get broken up by incoming photons of light. They undergo sublimation, where you have that phase change straight from solid to gas. So all the water exists in a gaseous state. Not much of it, right? It's a near vacuum, but there'd be little individual H2O molecules out there. What about when you go further out? Well, as you get further in the solar system, water, like a little ice crystal, can stay as an ice crystal because there's so much less sunlight out at a certain distance that the coldness of space dominates over the intensity of the sunlight. And that's the key difference. So I kind of, I said I wouldn't get into it, but it just felt like it was too potentially confusing to not at least explain it a little bit. Okay? Yep. And just being large isn't enough, at least not large size. And even large mass isn't enough. They have to be both large and cold. Because if you think about just, atmospheric retention, that's where the coldness comes in. Okay? Which is great, right? But even that's just part of the story. Because what was I just talking about? I was talking about the accretion itself. Accretion being that word for building a planet in the first place. So you've got accretion, then you've also, which is formation of the solar system, but then you've also got the how do they continue to exist? Well, they continue to exist. They continue to have these atmospheres because they're currently cold as well. Why are they currently cold? Because they're far from the sun. So that's another way to think about it, right? If you took Jupiter and you just pulled it in and you brought it so it was close to the sun, it would start to evaporate. It would start to lose its atmosphere because it would be too hot. And the average thermal speed of hydrogen, for example, would be greater than the escape velocity. Okay? So it'd have to be pretty close, though, because they're already so big that their escape velocities have grown to be, really strong, really significant, which is actually cool because it explains these things called hot Jupiters, which exist around other stars. Okay, but now we do need to break. So let's leave off here of why do they look so different, and we'll come back in 5 minutes to finish up chapter 11. Going to pause everything on my end. I'll check the chat when I get back. I gotta run real fast. All right, so continuing to talk about our Jovian planets and their generalizations. We have a question here that's going to make us collect our thoughts, and that is how, or rather why, do they look so different? How do we end up with bands on Jupiter, a ring on Saturn, and the colors of Uranus and Neptune? Because if you just look at their hydrogen and helium, they're pretty much the same, right? There's some variation in the amount of hydrogen and helium, but not significant differences to explain their almost said surface variation, but their upper cloud layer variation. So the look of the gas giants, the look of the Jovian worlds, is all to do with the trace molecules that exist. And those are going to be methane and ammonia, which are almost non-existent on Jupiter, and that has to do with how that Jupiter is the closest to the sun. It's a little bit too hot where Jupiter is to hold on to methane and ammonia in the upper cloud layers of that planet. But Saturn has a little bit, and Uranus and Neptune have trace amounts or significant amounts of methane and trace amounts of ammonia. So when we look at our cloud layers, we can say that the clouds of Jupiter and Saturn are composed largely of frozen ammonia, and the clouds of Uranus and Neptune are frozen methane. So that's what dominates the colors. So the blue color that's shared by both Neptune and Uranus, where Uranus is a much cooler blue, a much lighter blue, that is, and there's the darker characteristic blue of Neptune, as kind of the name implies, right? Watercolored. Well, that's going to be from methane. So remember, the blue ones come from methane, and then all the variations are based off of ammonia molecules for Jupiter and Saturn. How can ammonia define the look of Jupiter if it's trace amounts? Well, there's still enough, and it's just such a big planet that trace amounts can still be significant, significant in their actual number of molecules. So the colors are caused by the chemical reactions in the atmosphere, with these being the key building block molecules, methane and ammonia. All right, and then the chemical reactions that occur, of course, depend on temperature. So different temperature environments facilitate different chemical reactions, thus different larger molecules that form based on methane and ammonia. So methane freezes at 91 Kelvin. So that's why we have frozen methane for the two ice giants. See why the name makes sense. And no frozen methane for Jupiter and Saturn. So key difference right there, right? Below the freezing point at the upper cloud layer, because this temperature refers to the upper cloud layer, right? Obviously, it's not referring to an internal temperature. It's referring to kind of what is in this discussion a stand-in for this surface. It's just think of it as where the planet meets space. So that's what I keep calling the upper cloud layer. So that's the temperature. Upper atmosphere would be another name for it. Okay. And when we look at the rotation period, well, then we can actually consider another factor, which I was tempted to kind of bring up earlier, but I knew I wanted to wait until the time came, and that's the rotation speed. Because we saw when we looked at the characteristics that these planets have short days, right? They turn fast. And that really means that they must really be like moving quickly in a translational sense, like an actual, like if you were on the surface, how fast would you be moving forward? Well, to get the rotational speed, you would relate the rotational period to the radius and then calculate the rotational speed. You would use essentially the centripetal velocity formula to do that. And then if you put it in miles per hour for some reason instead of kilometers, but it's good for thinking about speeds, I suppose, then this refers to the speed at the edge of the atmosphere. Although that's a little vague. What it really means is the speed at the equator at the edge of the atmosphere. So this would be the equatorial upper cloud layer speed. So let's see, this one's turned outside and it's rotating counterclockwise. That would look like this. I had to think about it. And then it's going to be like this. Okay. So these are going to be, all of these arrows would correspond to these speeds. That's how fast they're actually moving around. And that speed is relative to the center of the planet. 28,000 for Jupiter, 22,000 for Saturn, 5,600, 6,000, all in miles per hour. These are incredibly fast speeds. And so it means that the centripetal force actually matters, whereas it can basically just be ignored for a planet like Earth. The centripetal force contribution to the total force you feel at the equator is less than 0.1%. Gravity dominates without question. Gravity still dominates without question for these worlds, but the centripetal force ends up being enough that you can't ignore it, especially at the equator. And that actually creates a bulging effect at the equator. All of the gas giants are noticeably wider equatorially. In terms of the energy exchange happening within the planets, convection is key. These planets, they're all, they become rather solid as we go down, as we talked about. But as I said, they're all about these layers that gradually transition. So there's huge amounts of volume of liquid and gas phases of matter, which allow for very significant amounts of heat moving in the form of convection, because convection is the heat exchange process that happens within fluids. Fluids is a term that refers to either a liquid or a gas. It's the combined name given to both of them, because unlike a solid, liquids and gases collectively have a lot in common, right? They behave in similar ways, especially in terms of how they move heat from one point to another. So convection, probably heard of it. It's all about the idea of hot things rising and cool things sinking. So if you got hot air, it's going to move upwards. As it moves upwards, it will cool. Then as it cools, it then is able to sink back down. So this process of convection is driven by the properties of gases and liquids, and of course gravity. Okay, because that's what's kind of keeping the loop going. Pulling the cool air back down is gravity, and the lower density of a pocket of hot air brings it back up. This happens in our own atmosphere. Convection is super important for the processes of weather that happen in our atmosphere. It's also incredibly important on Earth for what happens within the mantle or the outer core. It's going to be important when we talk about energy flow within the sun. So convection is a common topic that really transcends a lot of different systems. So when you have a convection process happening, which is a up and down process, right? So this is in, direction of gravity is this way. Well, when you have this process happening on a world, it's happening, of course, on a spherical body, and that spherical body is rotating. And so that means that the convection cell, which is the name of this loop, right? So it's called a cell because the loop forms kind of an enclosed area. That enclosed area is called the convection cell. Well, those cells get stretched over the planet due to the rotation. And so then you end up with convection cells, which, yes, are up and down, but when seen from above, are noticeable on a left and right or west, west, north, east, and south direction on the surface, on that curved surface. So that creates, the Coriolis effect on Earth and creates all types of gas flows on the Jovian planets and leads to these things called the Jovian bands, which are convection and rapid rotation conspiring to set up zonal flow. Okay, so the bands that we see, which are so noticeable on Jupiter, so much noticeable on Saturn, and subtle on Uranus and Neptune, are created because of that combination of vertical convection with lateral rotation. So Jupiter's light bands are from upward flowing warm gas, and the dark bands from downward flowing cool gas. So I won't check chat for this one, but we'll feel free to answer it. How do we measure the atmospheric rotation of the giant planets? Do we track a single feature on its surface? Do you measure the wind speed at the equator? Do you measure the variation in radio signals in the planet's interior? Or is it just impossible? Because in other words, how do you separate, rotation from, the wind speed? Because we see here, right, that we have, these significant variations in speed, right? Because this is the eastward wind speed, separate from rotation. All right, so you just need to find a fixed feature. So if you track a single feature on its surface, then that feature will be moving with the rotation. And that's going to be separate from the interior rotation, because after all, it's a fluid, so they move at different rates. So you can clearly see, right, these different bands moving at different rates. That central one moving really quickly. I know the animation is so fast, it kind of makes you dizzy. The slower band above it. And if you look up towards the pole, you can see the much slower bands. The great red spot is really kind of gradually moving along. So different parts of the atmosphere rotate at different rates. There's not one rotational value. There's literally a dynamic system of different rotation happening, all moving around a core that it has its own fixed value. All right. Oh, it's talking about the history of radio signals. We briefly talked about this when we talked about radio transmissions before. And this led to radio signals coming from Jupiter. So historically speaking, well, what was making them? Why were there radio signals coming from Jupiter? Well, it has to do with Jupiter's aurora borealis and its magnetic field, right? So Jupiter acting like an antenna. The great red spot on Jupiter, we saw it in the animation. It's a huge stable storm that rotates much slower than the bands, as we saw. Thought to last for hundreds of years, has been changing gradually since human observation, high quality human observation of it, began, and certainly isn't expected to last forever. Presumably humans will still be around in a couple hundred years, and there will be no more red spot. There are other high pressure storms, like these ones that are like kind of coming off of the great red spot, other ones that will persist for decades, merging together. It's a constant process. Saturn also has storms, but they're not as dramatic. Talking about one here in 2010, a vortex emerged on Saturn as the strong wind speeds pulled the storm around the planet. And then it sort of collapsed in on its own tail. There is a stable hexagonal vortex at Saturn's pole, but it doesn't get seen that much because a lot of our imaging includes the equator. But here, this image, false colored, so not true visible light, but showing other wavelengths, but clearly shows the shape, the hexagonal shape of the vortex. The center is more circular, but it has these real defined, angles to them. They're soft, right? But it's like a soft edged hexagon. There are also storms on Neptune. It's less observed. It's further out. Fewer missions have flown by it. But the Voyager 2, which shows us, kind of how few flyby missions we've had, considering that this mission was over 40 years ago, spotted a dark spot on Neptune. The storm, or a different one, has moved and changed sizes in images taken by Hubble since. This shows cirrus clouds, so high altitude clouds on Neptune. Notice that we didn't mention any storms on Uranus. Uranus is incredibly cold and just doesn't have enough energy to stimulate any upper cloud activity. The upper clouds of Uranus are just still, stagnant, not moving around at all. So Uranus has seemingly just lost a lot of internal energy, which may have to do with why it's on its side, and therefore is, first of all, much colder than Neptune in terms of the infrared radiation that comes off of Uranus shows a much colder planet, and that colder planet manifests itself in a very still atmosphere. So on to the magnetospheres of the planets. They all have magnetic fields. Where do they come from? So first, what are they, and how far do they extend into space? So the regions around a planet where the magnetic field created by the planet is the dominant magnetic field is the definition of the magnetosphere. So once you extend beyond the magnetosphere, the dominant magnetic effect would be that of the sun. So that's what sets the boundary. The sun itself has its own boundary of magnetic effects, which is the heliopause, and that's way out past the Kuiper belt. So which planets have magnetic fields? Okay, we know that Earth does, right? Talked about that. Jupiter, Saturn, Uranus, Neptune all have magnetic fields, okay? Of course, we learned that Mercury has a weak one, but here, this slide has decided to ignore it. Okay, review. Earth's magnetosphere, mostly aligned with the geographic poles, right? Deflects some harmful radiation from the sun, causes the auroras. Good key points there. Okay, so now let's talk about the new ones. Jupiter. It has magnetic field tilted away from the rotation axis, but not significantly, right? 10 degrees off the rotation axis, right? Although that isn't quite as aligned as ours, but still, close. Okay. It has a north pole at its geographic north, unlike ours. Of course, that means if you had a compass, the north of the compass would point towards the south pole of Jupiter. So we got that same old contradiction. You can't have it both ways. Okay, but regardless, this is the orientation of Jupiter's magnetic field. I don't know if there's any speculation if it flips like Earth's. I think it would be largely supposed that it does, but I don't think there's any direct evidence that we have showing that. We could have it in the future if we maybe were able to take rock samples from one of the moons of Jupiter, actually, show a history of the magnetic field. But I don't think we have any, because I know we haven't taken any rock samples from any moons of Jupiter. And so I would assume that there's no direct knowledge showing any history of flips. Because remember that we can look at the mid-ocean ridges on Earth and actually see a geological record that shows our own magnetic field flipping regularly. Moving on to Saturn's magnetosphere and its magnetic field, it is very aligned with the rotation axis. So almost perfectly, all right? It's also flipped over relative to Earth. All right. Now on to Uranus and Neptune, which are going to be totally different. They both have magnetic fields that are not aligned with the rotation axis and not even at the center of the planet. So we have a magnetic field that is centered near the pole for Uranus and is 60 degrees from the rotation axis. So what exactly is creating that magnetic field is not entirely clear, although it does seem to have something to do with the ice, the significant amount of methane and ammonia ice in the interior of the planet. Neptune is similar, 46 degrees from rotation axis and not centered. So see, another way that Uranus and Neptune group together with in this case, with their magnetic fields being off-center and tilted, and in that being a contrast to Jupiter and Saturn's magnetic fields. And the key that we want to think about is that these magnetic fields are created by different mechanisms. In the case of Jupiter and Saturn, the mechanism is going to be the metallic hydrogen, probably acting with similar properties comparable to an electromagnet, like with Earth's explanation of the magnetic field. Not the case with Uranus and Neptune, probably some sort of circulation, maybe not having to do with rotation at all, potentially, and happening with those ices, because the ices form ions, which is why they're the probable candidate for creating the current that's necessary for the magnetic field. So we would say that the ionic ices of methane and ammonia on Uranus and Neptune are responsible for their magnetic fields. What role do the Jovian planets play in the solar system? All right, well, here they are, right, to scale. All right, you can see their vast size in comparison to the much narrow region occupied by the terrestrial planets. So in terms of the space of the solar system that the orbits of the Jovian planets occupy is much bigger, right, than the terrestrial planets. It's just terrestrial planets are squeezed in close to the sun. There are these small little leftovers in this particular region. And then, if you were to take a bird's eye view, the solar system would look mostly like it's occupied by the Jovian planets. Neptune has an interesting history because it's the only planet that was discovered indirectly. So up through Uranus, all of those planets were observed by ancient peoples up into modern times with naked eye observation originally with the ancient peoples, and even going into the early era of telescopes, those planets were seen. All right, observed, documented, we knew about all of them. But it wasn't until the late 1700s that Neptune was confirmed with a telescope, but it was speculated before then because of its pull on Uranus and the affecting pull back from Uranus. So basically, because of the way that Uranus orbited and the fact that that orbit didn't make sense unless another significant mass was pulling on it, was how scientists knew where to look, right? Earliest, 18th century astronomers, so 1700s, that's how they knew where to look and eventually confirmed the existence of Neptune, which they originally named after the British king at the time. So they called it George's planet. And it was called Georgia. But then after a decade or two, they changed the name. But originally it was named Georgia. All right, so seasons on Earth, what are they caused by? All right, well, they're caused by the tilt. It's the axial tilt, not the elliptical orbit, the axial tilt. So does that mean that we should expect seasons on the Jovian planets? Well, the tilt of Jupiter is almost non-existent. So that means that there'd be almost no change in flux, thus no significant seasons. On Saturn, we do have significant seasons, all right, with a 15-year cycle between them. So about 15 years between Earth years, at least, between a Saturn summer and a Saturn winter, depending on which hemisphere you're in. Okay? Of course, the total change is much less significant because the distance from the sun makes that total change less. As you get further away, the changing between a little bit of flux and then a little bit less than a little flux isn't that big of a deal. All right. And then can we see direct effects, say, in the storms and the behavior of that convection? And the jury is still out, right? And that is certainly true with a lot of the observations that would require variation over orbital periods. Imagine trying to study the variation in Uranus and Neptune with, in the case of Neptune, an orbit that's 160 years. Well, it's going to be quite a few human generations before we have enough data to make conclusive results, or to make conclusions from our results. Okay, and then talking about who's experiencing winter. I think you're familiar with that idea, right? If you're facing away from the sun, if you're in the hemisphere that's facing away from the sun, then you experience winter, which is why our person up here in the clouds of Saturn experiences winter at this point in Saturn's orbit. Now, Uranus, with its strange tilt, certainly demands the question, what would its seasons be like? Or what are its seasons like? Well, to go from this orientation, where the North Pole is facing almost directly away from the sun, to this point, where the North Pole is facing directly towards the sun, nearly, is about 42 years. Okay, so to go from a North Pole, I guess you could say winter, but extreme, to an extreme summer, 42-year difference. So that means that there definitely are going to be some extreme changes in the flux with darkness for half of the year of Uranus. And when we say half of the year, again, it's the year of Uranus, which is a long time. So the pole of this planet is going to have no sunlight reaching it for many Earth years. Right? We talk about our own poles not having sunlight for a month or two at a time, 3 months in the ideal case. Well, lots of twilight. Then, imagine that extended tenfold and more than that. All right, seasons on Neptune, definitely there with 82 years between a summer and a winter because the axial tilt is, pretty well defined. But the difference is so small because Neptune is so far away. And that concludes this lecture on the Jovian planets. And I'm going to spend the next couple minutes just squeezing a little bit of a start on 12 because I want to use what available time we can.